All right, so let's talk about the secret of the ellipse. Um, Last time I mentioned that anytime you have a potential energy that's the square of a coordinate, like x squared, or as we say in the physics business, quadratic, you're going to have an oscillating system. And hey, you guys, it could even be an angle. An angle's a kind of a coordinate. And so if you have something that's, got theta squared in it, yeah, that could be an oscillating system. Matter of fact, the pendulum uh, can be styled as an oscillator in which the coordinate that uh, spans the oscillation is theta, the swing angle of the pendulum. Now, when we were doing this, Kamari held the pendulum out about 12 inches, 10 inches or so, and then let it swing. And we approximated that as a flat X oscillation. And I said, it's pretty close to the actual curving arc. But yeah, you can actually use the curving arc of the pendulum as your oscillation. You'll find that stuff. So anytime you have something that's quadratic, you're looking at an oscillating system. Now, the thing I want to concentrate on for the first half of class today is phase space. And as we mentioned last time, the representation of the entire motion of an oscillator, Megan, can be represented as an ellipse in phase space. And I've got one mapped out here. The bounds of the ellipse are the following. So if you have maximum compression, so if we're thinking about this as a spring, max compression to the left, that will correspond to this dashed line over here, see on the left of the ellipse. All right, the ellipse doesn't range anywhere further to the left than that. Now, on the right side, you would have the max extension, x subscript r. And that's the notation that we used last time. Point R was over here, more towards the front of the lectern, and point L was over there where Kamari was holding the, where he started the oscillation. Okay, so that's the maximum left-right, max extension for maximum rightward, max compression for maximum leftward. The other thing that you can do, so here are the two boundary lines, another boundary line there on the right side. The other thing you can have is the ellipse is contained by vertical boundaries. So maximum rightward momentum, that will correspond to this upper dashed line. All right, for P max, maximum rightward value of the momentum. So MV is positive if you're moving to the right. And you're moving to the right at your highest speed at x equals 0, at the equilibrium point. There's no force there for just that instant, Sabrina, but you still have attained your highest speed. And then as soon as you pass equilibrium, you start slowing down again. And you start slowing down, and you turn around and you bounce back and forth, you oscillate. The other boundary below the ellipse is maximum leftward momentum. So that's going to be a negative number. So if P max is, like 1.73 kilogram meters per second, then negative P max will be negative 1.73 kilogram meters per second. All right, and so that's this boundary line below. And so the phase space representation of any oscillating system, whether it's a spring or an electron in a crystal lattice or a wave in the ocean, it might not be a perfect ellipse in the case of a wave in the ocean, but it'll be close to a perfect ellipse, and many physical systems are perfect ellipses. Right? The spring system is a perfect ellipse. By the way, if you've ever been to the doctor's office and taken an EKG for your heart, a lot of times what a doctor will do is he will represent the motion of your heart, the beating motion of your heart in phase space. And a good, solid heartbeat, nice and regular, no irregularities, will have an elliptical shape in phase space. A heart that's in defibrillation will be all over the place in phase space. It just will be all discombobulated. And so a lot of times a cardiologist, well, my little sister is an electrocardiologist. And so what they do is they look at phase space sometimes to study the structure of someone's, or the health of someone's heart, to see what's actually happening. It can reveal a lot. The other thing I want to mention to you is, and this is actually where the secret of the ellipse comes in, the area of the ellipse, every enclosed figure, whether it's an ellipse or a triangle or a square or, a pentagon or a hexagon, is going to have some area. It's going to enclose some area. The physical meaning of the ellipse area is what we're going to tackle today. That's the secret of the ellipse. And that area is measured in units of angular momentum, kilogram meter squared per second. And in fancy terminology, those are also the units of action. A joule second or a kilogram meter squared per second. The units of action. Now here's the same ellipse. Let me just make it a little bit bigger. Okay, here's the left boundary, and here's x subscript L for the x coordinate, leftmost x position for this particular oscillator, whatever it is we're looking at. Similarly, on the other side, x subscript R marks the rightward boundary. Now let me emphasize and add this to your notes. This is not a strobe photograph. This is not a picture. It is an abstract representation. You cannot take a photograph of momentum. You can't, if you're traveling down the turnpike heading for Miami, you can look at mile markers, mile marker 107, mile marker 108, you're headed for the Turkey Neck Service Plaza. You look at the mile markers. So how far do I get, to the Turkey Neck Service Plaza, et cetera, et cetera. There's no kilogram meter per second markers. We wouldn't know how to set them up. And so you can't really photograph those. Similarly, if you're out there by the side of the road and you take a picture of a car going by and your camera's aimed down the road, your photograph, you could measure it, do some triangulation and stuff, and figure, a certain point on your photograph is, like 1.5 kilometers away from you. Do a little trig and right triangles and all that stuff, and and that's what they got guys down there at the Pentagon doing. They're looking at photographs of the Russians from space, and they work out all the angles and the trig and figure out, well, okay, this tank is 15.5 meters wide or long or whatever the size of it is. And you can do that with photographs. This is not a photograph. Okay? You can't take a camera and take a photograph of this. So do not be deceived. This is an abstract representation of the motion. Also, not on this graph is the direction of time. I haven't, we did it on Thursday, but I don't have it here. But Kamari started it over here on the left, and then it traveled to the right. So the direction of time was clockwise on the ellipse. And we put a couple arrows on there. Now the upper boundary, here it is, P subscript max, maximum momentum. And I actually asked you about that in the clicker question, the brain burner. Here's the lower limit, negative P max. And they're symmetric. If it's a good oscillator, it'll be symmetric. It'll be a perfect ellipse. A heart on a phase portrait of a heart that's beating, even a good sound heartbeat, it's not going to be a perfect ellipse. It'll look a little bit like this, but it won't have the exact mathematical formula for an ellipse. But it'll be close. It'll look close to this. By the way, I was watching this old-timey TV show on MeTV, channel 2.2, Emergency. And it's the TV show about two guys that are in charge of a EMT truck. And they go around saving people's lives and stuff. And so they're talking over the radio back to the hospital, and they got all the doctors and nurses at the hospital listening on the radio. And you know, the two EMTs are saying, yeah, we got a sinus rhythm. Sinus rhythm. S-I-N-U-S. Now that doesn't mean they have sinus, you know, like up here in your coconut. Sinus rhythm means a nice curve. Sinusoidal. That's a trig term. What they're saying is that you've got, you know, like on the when you're in the ICU and they show the, you know, the little heartbeat curve, and it's nice and even, up and down and up and down. That's a sinusoidal rhythm. A sinusoidal rhythm in the heartbeat is going to correspond to an ellipse or close to an ellipse. A perfect sinusoidal heartbeat, you know, theoretically would be a perfect ellipse. But any heartbeat's going to look something like this. All right. Now, I want to shove this over to the side a little bit. Here we go. Let's kind of park it over here. I want to point out something that we talked about last time, and that is the area of the ellipse. The area has physical significance for us, and I mentioned last time that it's equal to pi times half the widest side times half the narrowest side. All right? So for this ellipse, the narrow distance is top to bottom, so half of that distance, and then the widest distance is left to right, so half of that. Now the formula for that would basically be this in terms of this particular diagram: pi times half the width, so that's the xr coordinate. Okay, so if this is 0 right here at the center of the ellipse, okay, 0, 0, then xr is like, you know, 0.32 meters or something. All right, and that's half the width of the ellipse. And then half the height is from 0, 0 here at the origin, Elizabeth, all the way up to P max. So that could be like 4.75 kilogram meters per second, or, you know, whatever it works out to be. All right. Now, instead of putting numbers in there, I did a little bit of algebra. You can jot this formula down. It's not that fancy looking, but it's kind of interesting. We're not really going to use this one too much, except to just look at it. You're not going to have to, I'm not going to put this on the cover page of exam 3. You're not going to have to calculate it. But it is kind of interesting that XR comes in 2 times in the area. Once from the, you know, the width, XR is half the width. And then maximum momentum also contains a factor of XR, because the further you pull it out to the right or to the left to start, the more momentum you're going to have when it crosses equilibrium. So if you just budget out by a centimeter, it's going to have some momentum when it crosses equilibrium, but it won't be much. But if you pull it out 20 centimeters, 0.20 meters, you're going to have a lot of momentum when it comes across x equals 0, the equilibrium. All right? So that's why XR comes in here as the square. Now, that should get you thinking. When you see the square of a coordinate, what should you be thinking? Oscillation. And what does the square of a coordinate in an oscillator allow you to calculate? It's quadratic. It's the square. Spring potential energy. So we should be thinking energy here. All right? Oh, nice. All right? So what I'm going to do is I'm going to factor out a k out of that square root. But look at this stuff here. mk inside of a square root? What? What the dickens is that? As they say, there's this famous phrase in physics, who ordered that? The square root of mk. That's like somebody, you get a pizza and it arrives with anchovies on it. And somebody's, I don't like anchovies. I'm not going to ask for a show of hands, but if you like anchovies, I'm about to say something that might shock you. But if somebody ordered a pizza and it arrived with anchovies, I would have to say, who ordered anchovies, The same thing here. Who ordered square root of mk? Oh, yuck. But it's going to be nice eventually. And the reason is this xr squared is the tip-off. I'm going to factor a k out of the square root, and that changes the square root into m over k square rooted. And then I'm going to put in a factor 1/2 here, and now, Abigail, it does look like spring potential energy, 1/2 kx squared, xr quantity squared. And I put a factor of 2 out here. So I insert an extra factor 1/2, Taylor, right over here. And then I put another factor 2 over here. So I haven't changed anything. I've made things look a little different, but if you calculate everything, it's still the same value. Multiplied by 2, multiplied by half is equal to 1. So I'm just multiplying by 1. I'm not changing anything. But DJ, I'm rearranging the furniture a little bit so that I can see that I've got an energy here. And that's the thing. For us, 1/2 k xr squared is the total mechanical energy. And we love energy. Energy is my friend. Energy is a dynamical quantity that rules the universe. So we like this. It's nice. It's lovely. But I still got those anchovies in there. The square root of k over m. What? The square root of m over k. What is that? Bull. Oh, so you got this thing here. Oh, yuck. Brr. What the? Square root of mk? Bad. Square root of m over. So this is like anchovies in olive oil sauce or something, that's technically, oh, you know what else? They got this stuff, anchovies. And so you don't want to have pizza with anchovies. Another thing you don't want on your pizza is lutefisk. Lutefisk is this stuff from like Norway where I tried it once. It's bad. But if you're from Norway, people love it. Raise your hand if you've ever, no, I take that back. I don't want to show of hands of people that like lutefisk. Hopefully you never have to encounter lutefisk. But if you ever go to Norway, they're crazy about it. And that's what we got here. Square root of m over k, lutefisk, yuck. But we're going to deal with it. Abigail.
How do you feel about pineapple on pizza? Oh, God, why?
Oh, pineapple on pizza. Fine. I happen to like pineapple on pizza. And many people, I know, many people that, there's many people that are haters. And I try not to do any of that. I like pineapple on pizza. I like almost anything on pizza, actually. Except anchovies and lutefisk. Anyway, so what we're going to tackle, we're not going to tackle lutefisk here, square root of m over k. What we're going to tackle is square root k over m, the reciprocal of it. And what we're going to find is that it's not lutefisk, it's not anchovies, it's something delicious. So think of the most delicious, if you've ever been to like Red Lobster where they serve seafood and stuff, the most delicious thing you've ever had at Red Lobster. You know, like lobster tails or something like that. Okay, what we're going to find is that square root k over m is really nice. But we got to analyze it. All right? So we're going to target this one, and then we're going to say to ourselves, okay, my area formula, I've got energy, which I like, and then I've got this square root of m over k, and the reciprocal of that is k over m. So if I can figure out what the reciprocal means, I can figure out why it's in this formula for the area. All right? So here we go. All right? Now, let's look at the units of the spring constant K. All right? Newtons per meter. It's the stretch factor. You know, how hard is it to stretch a spring? Newtons per meter. All right? Now, Newton is the same as, okay, here the second line of my first equation block. The numerator is kilogram meters per second squared. That's a Newton in, Jasmine, in fundamental units. Kilogram meter per second squared. Okay, we've used that quite a bit. All right. And then I've got meters down here. So newtons per meter is, okay, in fundamental units, kilogram meter per second squared. Now, we got meters top and bottom. You see them? Ching! Go ahead and burn those babies off. Okay, we can cancel them, Mivosh. And now my factor K, all right, this is still anchovy. I mean, this is still a little bit yucky looking. Kilogram per second squared. What? What is that? All right. So hold on tight. We're going to get to it. It's going to make sense in just a second. Now, the other part of the anchovy square root is m, mass. Now, that one's pretty cinchy. That's just kilograms. The units of measure for mass are just kilograms. So that's good. Okay, Ariza? Good. Ariza. Now, we're going to put those two together. Here they are, K over M. That's the inside of the square root that we're trying to attack, Bobby. And so let's put it together. So here's what I got. Okay, my kilogram per second squared, that goes in the numerator up here. That's this first arrow over to my third equation block. And then, okay, kilogram, ching, that goes in the denominator. So that's cinchy. Now, don't worry about having to do this on a test. You know, you just kind of follow along here. And we're walking. This is like going up a really steep part of the mountain. And if you just walk with me a little bit further, we're going to get up to the top of the steep part, and we're going to look at over a lovely view across the valley from part way up the mountain. Now, we're not at the top of the mountain yet, but we're heading there. All right. So anyways, here's my quotient. Kilogram per second squared on top, in the denominator, kilograms. And guess what? We can burn off kilograms. And when we do, we get 1 over second squared. Carolyn Cook, that is nice. 1 over second squared. Now I've just got seconds to the 2th power. All right? But remember, this is not my target. My target is the square root of this stuff. So then when you square root this, the units are 1 over seconds. My wonderful students, that is a hertz. And so this weird looking cane, this weird looking pile of anchovies has turned into a frequency. And we calculated a frequency on Thursday, Joshua. Hold on a second. Joshua, when we were here, Kamari got the thing going, and we timed it. We made time measurements. We figured out a frequency. Frequency is nice. Joshua, question.
What is the
Because my target is the square root of k over m. Okay, in the area formula, it's a square root that comes in. We're trying to, so it looks nasty, it looks bodacious, but actually, if you think about it, it's a frequency measured in hertz. Here we go. Area. Energy divided by frequency. And a factor of 2 pi out in front. And that, my wonderful students, is lovely. Because, hey, we can figure out a frequency. Time it out, good. Second comment about being able to measure it and then calculate measure the period and then figure the frequency, the period we came out, I don't know, what was it last time? About 2.2 something for the period? Go ahead and look at 2.22. And then our frequency was about 0.45. Right? So we can do that. But here's something I want to point out to you. And I want you to make a note. The frequency, omega, that curvaceous W, that's a Greek lowercase omega. Right? That frequency, omega, it doesn't have anything in there about initial condition XR or XL. It's just the machine itself, the spring K, and the mass attached to it. That's it. It is a property of the machine. You control the energy. Capital E, total energy, Anthony. You control it by how far out you pull it to start. You pull it out to 1 centimeter, good, a little bit of energy. Pull it out to 21 centimeters, nice, even more energy. Because remember, it's 1/2 kx squared. Right? So you're in charge of the energy. The machine is in charge of omega. Second comment. If you pull the oscillator out to 1 centimeter and let it go, it'll oscillate at this frequency. If you pull it out to 21 centimeters, it'll oscillate all the way out to negative 21 centimeters and back at the same frequency. It does not matter where you start the spring. Let me repeat that. It is a property of the spring mass system. It does not depend on where you start the spring. It's independent of initial conditions or the experiment. It's part of the machine. No matter where you start it, it'll oscillate at this frequency, and it'll take a certain amount of time, the period, like 2.2 seconds, 2.22 seconds that we measure, no matter what. Now, if you pull it out 1 centimeter, it's not going to be moving that fast. It's going to be kind of pokey. And it only has to go 2 meters across and then 2 meters back, or 2 centimeters across, 2 centimeters back. So it doesn't need a whole lot of speed to keep to that frequency and period. But if you pull it out to 21 centimeters, it's got a motate. Going through the center, going through x equals 0.0 meters, yeah, you got a motor. If you're going to get all the way over to negative 21 centimeters and all the way back to positive 21 centimeters in that same time period. But that's what springs do. It's kind of cool. This formula is extremely simple. It is the energy divided by a frequency. And what we're going to find is that the area of this ellipse for any oscillating system, it represents a dynamical quantity of enormous significance. This dynamical quantity is called the action. Planck's constant, the constant that rules the world, the quantum world of atoms and molecules, is a quantum of action. It's nature's fundamental unit of action. Action first makes its appearance here for an oscillator, but we're going to find that action and these kind of ellipses and diagrams in phase space will make sense of the atom and molecules that we observe, everything that we have seen. Now, question up here.
Last time we were talking about frequency use the lowercase f.
Yeah, I did, and I'm using an omega now, but you can, it's kind of interchangeable, okay? And we're not going to make a big deal about calculating it, but what we are going to make note of is the fact that, yeah, that is a frequency down there. So if I want to give it a symbol X, like, well, I wouldn't use X, but any symbol, as long as we know that it's a frequency down there in the ratio, it's very, very important. Okay, Kate. Kane is asking me, will I always give you E? The answer to that is no. I might give you the spring constant and the initial pull-out distance, left or right. But from that, you can calculate E and then figure all this stuff out. I've got to give you enough of information, like the design of the machine. I'd have to give you K and the mass M. Okay? Then I'd have to tell you the initial conditions. At rest, and X, initial position, XI equals, 0.17 meters or something like that. And you can figure out all the rest. You can figure out the area of the ellipse if you wanted to. Now, I'm not going to ask you to figure out ellipse areas. Not yet, anyways. But I want to make sure that you think about this picture and understand the importance of the area, that it is an area that we want to focus on. Yeah, for us, yeah. SPE at maximum extension, either left or right, that's also total kinetic, that's total energy. Question?
Oh, that's what I was going to ask. If you use kinetic or total.
Capital E is total mechanical energy. Remember, total mechanical energy, E equals SPE plus KE. Just like, when we were doing free fall, total mechanical energy E equals GPE plus KE. At every level. Right? So for an oscillator system, total energy is E at every horizontal distance, all the way out to maximum extension and all the way back. But the KE and the SPE changes by position. Third comment about the area of this ellipse. The area of this ellipse is directly related to the entropy of the system. ENTROPY. We have mentioned it before. We will mention it again. And by the end of the semester, you'll be thinking about the entropy of a quantum system. Hopefully. It is related. The area of this ellipse for an oscillating system is directly related to the entropy. And we'll get more in detail about that probably by the end of April. So we got another month to get up to that level. All right, now I want to, is there any other question about ellipses? The secret of the ellipse? Okay, let's continue onward. And just remember, the ellipse is not a photograph, but it is an abstract representation. It can't be photographed. It doesn't represent something that you could plot on graph paper and then photograph. But it is a dynamical quantity of vast importance. Now, last time we talked about the tuning forks. We demonstrated it. Darian and I, we took two tuning forks up here, and I struck one of the tuning forks while Darian had her hand on the second one. So the second one wasn't oscillating. You didn't do tuning forks? Ooh. There's a YouTube video. All right. Emergency homework. I'll link to. I thought I did that. So we just did the pendulum. We spent a lot of time with the pendulum. That was good. All right. Okay, side note. I'll put a link in homework tonight for you guys only. Well, for everybody. Because we have tuning fork. I think we have it resonance on YouTube.
Yeah, we should.
Do we? Okay.
I'll look.
Also, resonance. If you've ever, when you were like a little shrimpy kid in elementary school, gone on the swings, and you know how if you pump your feet, you pump your feet at just the right time, you can go really high. It's high enough to get yelled at by your third grade teacher if it's recess. And what we used to do, like in sixth grade, we used to get, pump and get as high as we could. And then when we got really high, we would let go and go flying. And I really hurt my knee one time doing that. But that's resonance. You can't do it unless you pump with your feet at exactly the right point of the swing arc. So that's an example of resonance. Right now, I forgot to do the tuning fork demonstration with you last time. We'll try to do that, and that's a resonance effect. We'll try to get a YouTube of it for you for homework. But I want to talk about another resonance event, which is extremely famous. The Tacoma Narrows Bridge disaster, which back in the early 1940s was a bridge. In fact, it was a pretty new bridge that was notorious for catching the wind when the wind was just right and starting to oscillate, from one end of the bridge to the other. And it actually oscillated sides, it kind of twisted. Okay? And I'm going to show you a picture of the twist. This picture that you're looking at right here is a picture of it just after it collapsed. The concrete and steel eventually failed, and down she goes. All right, catastrophic collapse. Engineers all over the world, really dig Tacoma Narrows Bridge because it's a catastrophe. They enjoy everything that blows up and stuff. And this is a famous one that they actually caught on film. So jot that down. Go into YouTube and or Google, and you see tons of pictures and talk and discussions and videos and stuff. And this is a case of resonance. In other words, it was a bridge designed to just be in one configuration, but when the wind was just right, it would start to oscillate. And if it's at the right speed and the right direction, just like when you're on the swings at school in third grade and you just do it at just the right speed, you can get maximum swing. Same thing here. When the wind is in the right direction at the right speed and when the atmospheric pressure is just right, something called standing waves form. Standing waves. And we're going to demonstrate this in just a second, Caroline and I. And the standing waves form, and they get bigger and bigger and bigger. And eventually the amplitude of the oscillation is so big, measured in feet. So it's not a shrimpy little oscillation. When you go across a bridge, you can feel if a truck is behind you, you can feel that the truck, causes the bridge to rumble a little bit. But in this case, it's ginormous. And when that happened, the bridge, was destroyed. It just blew apart. And you can see this photograph. Now, here's a couple photographs. I want you to look at this. Okay, so here's the picture. Look at this. Look. No, not at your computer. Look at this. Come on, you guys. White t-shirt. Come on, look. White t-shirt man. Yeah, good. Look at this. This is looking from one end to the other. It's from a film, one of the films they took. You see that car out there? It's this little car right here. See it there? It's kind of hard to see. If you look at it on YouTube, you'll see it. It's clear as a bell. Right? There's some guy that drove out on the bridge, and when he realized what was happening, he bailed out of his car and he ran to the other side of the bridge. But you know what? He left his dog in the car. What a jerk. But thank God there was a physics professor at the other end, at this end, and that physics professor ran out there and got the dog. But now, this is what was happening. There was, from one end of the bridge, it was looking like this, wave, standing wave. And it was also twisting. So a second later, this is what it looked like. Oh my goodness. Talk about seasick. You think you could run out there? But that one guy did. He's on the film. He went out there to get that little pooch. I think he got it too. Anyways, Tacoma Narrows Bridge, famous resonance, and an example of standing waves that led to a catastrophic collapse. Now, what Carolyn and I are going to do is we're going to do standing waves demonstration, and I want you to take notes and make sketches of what we're about to do. Okay, and I'm going to do the same thing in theory. Now I'm going to stand here so that I'm going to stand here, and what I'm going to do is I'm going to oscillate this end of the spring. Back a step. Now the distance from my hand to Caroline is maybe 10 feet. That's our baseline distance. And what I'm going to do is I'm going to send a wave across from me to Caroline. Look. And what does it do? It reflects from Caroline's hand and it comes back towards me. Now, if I do this, that was just one. Do it again. Goes out, comes back. Now, what if I just keep going? Go at the right rate. I'm sending waves. Every time I oscillate my hand, I'm sending a wave to Caroline. Every time that wave gets to Caroline, it comes back towards me. Does anything look like it's moving left or right? This is a standing wave. Make a sketch of it. This is called the fundamental mode of this oscillating system. It is a bump oscillating with a dip. If I just get now if I speed up a little bit, see it's all discombobulated. So I have to have the right frequency. See if I can get it back. There it is. Right. Fundamental mode. Make a sketch of it. Now I'm going to change the frequency and see if I can get another standing wave. Right? And this one's going to be closer to the Tacoma Narrows Bridge wave. Okay? And by the way, if you ever think of like the Golden Gate Bridge or any suspension bridge, there's two big piers or towers. And the bridge is suspended between those two towers. The two towers are like Caroline and me. The bridge will oscillate between those, if it oscillates, it's going to oscillate between those two fixed points. Okay? So let me try this again. Let's see if I can get. All right, here's fundamental. All right, now oh. There it is. This is the first excited state. A bump and a dip oscillating to a dip and a bump. Make a sketch of it. And notice that there's one bump and one dip. Is it moving to the left or right? Yes, but it doesn't appear to be. It appears to be in one place. Waves are moving from me towards Carolyn, from Carolyn back towards me, but it doesn't look like it. It's just kind of sitting there. If you ever go canoeing in a river where there are rapids, sometimes see big standing waves called haystacks. Oh my goodness. Those are really fun. Okay, first excited state. Now let me change to a little bit different frequency. See if I can get another one. Okay, another standing wave mode that has more bumps and dips. Okay, that one had a bump and a dip. Let's see if I can get one with 2 bumps and a dip, or 2 dips and a bump. You gotta get it. Is that it? Is that? No, it's kind of. Oh! All right, make it. It's rotating.
It's spinning.
It's spinning, but it's 2 bumps and a dip, oscillating with 2 dips and a bump. Make a sketch of it. This is the second excited state. It's actually rotating as well. Actually, it's kind of cool because radiation does that. Electromagnetic radiation has circular polarizations. Yeah. Now it's oscillating. Ooh. It's oscillating left to right. Ooh, Dr. B. Sideways. You gotta get this right. There it is. Second excited state. Okay, 2 bumps oscillating with a dip. Okay, let's go. All right, now I'm going to ask you some clicker questions about this. So I hope you took good notes. We'll change that. All right. Okay. Before we get to the clicker questions, just a little bit of nomenclature. Wavelength. Usual symbol is Greek lowercase lambda. It looks like an upside down Y. The wavelength is the physical measurement, spatial measurement, in centimeters or meters, nanometers, from peak to peak, as I've got diagrammed out here. Now you can do it between any 2 peaks that you want. So look at my animation here. Take a look. You ready? Take a look. Okay? Just go over to that pair of peaks. That's kosher. Or, you could go, instead of peak to peak, how about dip to dip? Yeah. Trough to trough. There you go. That's the wavelength. So if you measure trough to trough, that's good. That'll give you the wavelength. So many meters. So now if you can only measure half of the wave, that's half a wavelength. A single bump is half the wavelength, lambda over 2. All right? So when Caroline and I were about 10 feet apart. And that fundamental mode, that's all we got. We got a bump oscillating with a dip. Now, this is the width of a bump. Now let's go to a dip. All right, here it is. There's the width of a dip, or the width of a trough, measured at sea level. Right? Measured at the equilibrium level. All right, or relative to equilibrium. Okay, so that's a couple different ways to look at the wavelength. Now I have some clicker questions I want to ask you. Okay, so get your clicker out and let's proceed. First the question, Kane. Kane is asking me, going back to the bridge, wouldn't it be faulty design? And the answer to that is yes. They didn't realize it when they built it. When you look at the videos on YouTube, you'll see that the sides of the bridge structure are enclosed by metal plates. You know, the bridge is basically a set of steel boxes, you know, welded and bolted together from one, and then held up by cables from one end of the bridge, one bank to the other bank. So, and that's how they fabricate it. Okay, a steel box, you know, so steel girders front and back, left and right, top and bottom, and then concrete for the road surface. Okay, and what they did with that is the sides of each box. So the left side of the road and the right side of the road, if you look, they had a steel plating. Not for some reason they decided to do that to protect it from the wind, but what they didn't realize was that made it into a sail, like a sailboat. And like a sail on a sailboat, it caught the wind. And it caused it to move and flex. And that's why they don't make bridges like that anymore. That one they did, and it was catastrophic failure. So if you look at any bridge that you go over, you're going to see that they try to minimize the amount of area facing into the prevailing wind. Okay, so they're not going to have sides that are steel plates. They might have a grid or something like that, but not flat steel plates. Okay, first question. Concerning the demonstration, now look at your diagrams, look at your notes. Which wave mode in the demonstration had the shorter wavelength? So a bump and a dip. Which one had the shortest beginning of bump to end of dip distance? That's a wavelength. Okay. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, good. Correct. Second excited state. And let's think about this for a second. So make some notes. You know, so this could be part of your. This question is like part of your notes. Comment number 1: fundamental mode oscillated between one bump and one dip. Okay, so that means that 10 feet from Caroline to me was the width of a bump, the width of a dip. That means 10 feet is lambda over 2. So for the fundamental mode, lambda is equal to 20 feet, approximately. So make a note of that. The second excited mode, we still got 10 feet. Caroline didn't move anywhere. But now we have a bump, a dip, and a bump. All right? So each bump or dip is half a wavelength. So we have 1.5 wavelengths between Carolyn and me. Right? So that means that, let's see, divide 10 feet into 3. Okay, 10 feet divided by 3 is 3 feet and a third. What's a third of a foot? 4 inches. Okay, so a third of it, 3 inches and 3 feet 4 inches. Multiply that by 2. 6 feet 8 inches. So the second excited state, lambda, 3 bumps for between Caroline and me. So that means 1.5 full waves. So that means each wave was 6 feet 8 inches. Right. Smaller wavelength. Fundamental was 10 feet for a single bump. Now, the first excited state was a bump and a dip. So the wavelength of the first excited state was exactly 10 feet. So that's kind of the middle, the intermediate value. Frequency. Second question, please. Which one had the smaller frequency? Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, good. Most of you got it right. A few of you voted for first excited state. No, if you noticed, I had to speed up my oscillation. That means bigger frequency in order to get to the first excited state. So that means fundamental mode. And side note, smallest frequency, biggest wavelength. Wavelength is 20. Frequency is smallest for fundamental. Now, let's talk about this idea of interference, the interference of waves. Interference of waves is actually behind the Tacoma Narrows Bridge disaster. It's behind resonance of sound waves that we'll link to on YouTube. It's behind a lot of stuff. Okay, so I want you to read in chapter 7. I think it's 7.5, the section on standing waves. And to have a standing wave or interference of any kind, you have to have at least two sources of waves. So, for instance, you could have a storm off the coast of West Africa and a storm off the coast of Nova Scotia, and somewhere in the middle of the Atlantic between the two, the waves from each storm are going to interact. Now, I should make a note before we discuss what happens. Waves transport energy and momentum. They do not transport the water across the Atlantic. Okay, we have currents in the ocean, like the Gulf Stream, but that's not wave motion. And you're going to see what happens with waves when they interact in the next few slides. Here's a picture, kind of idealized, of two bumps. One heading in from the west coast of Africa, one heading in from Nova Scotia. Where they meet, that's signified A plus B, you get a big rogue wave out in the middle of the ocean. Another place where there's wave effects like this, interference, Praia do Norte in Saint Nazaire, Portugal. Those waves are big because of that subterranean or that underwater canyon. When the waves are right, when the wind is right, they get gigantic waves. Same thing here. Now, after these waves interact, what happens to them? Are they dead? No. They just keep going on their merry way. B just keeps rotating off to the left, and A just keeps zipping, zapping over to the right. And that's because it's not water that's moving, it's energy and momentum. And they go right through each other. They interact. They get that big pile of water up there at the top of this slide. But they don't destroy each other. Matter of fact, this is what's called constructive interference. Constructive interference. They add together. A plus B is a big pile of water. Now, here's a variation on it. Another sketch that you can make. What happens when A and B, now this is at the bottom, I just took the picture, the previous picture, and flipped it upside down and relabeled it. So now A and B are coming, one from the coast of West Africa, one from the coast of Nova Scotia, and they meet, but they're dips, and they meet in the middle of the ocean somewhere, and now you have a gigantic trough. And in reality, the waves in the ocean are wave, crest, trough, crest, trough, crest, for hundreds of miles, trains of waves. And so it's not just, so this one's kind of idealized, two isolated troughs interacting. So in the real ocean, you'll get a series of really deep troughs. Okay, so if you ever watch, Discovery Channel or something like that, sometimes they'll have a show about rogue waves in the ocean that, they can capsize big cargo ships, stuff. Matter of fact, I read that ship that went down, El Faro, that cargo ship, and all those men were killed. Some people think it was a rogue wave that actually got them and broke the ship apart. Nobody will probably ever know. But now, this is trough to trough, and the previous one was peak to peak or crest to crest. What happens when a crest and a trough meet? All right, because this can happen too. A real wave train in the ocean, you got crests and troughs there. They're going to interact. So a crest from West Africa meets a trough from Nova Scotia. What happens? Well, this is what happens down here, flat water. For just an instant of time, when they interact at A plus B, the trough balances out the crest. Flat water. And my wonderful students, this is known as destructive interference. Now, the waves don't destroy it, but what does happen is the amplitude is momentarily zipped and zapped, all right? Because just a little bit later, they just keep motoring on. Wave B, trough B, is still heading for West Africa, and crest A is still heading for Nova Scotia. That energy hasn't disappeared, but for that moment in time, flat water, all right? Now, I hope you've made some good sketches. Let's go and make an outline of that. Okay, so two source waves. At certain points, you might have two wave crests. So that would be like Praia del Norte, super big surf. Or, further out in the ocean, a rogue wave that might tip over a boat. Hopefully not. At other points, you might have two troughs that meet, and then you have an extra deep trough. We have a sketch of that. At other points, you might get a crest and a trough that intersect, and there you have flat water, no wave. Right? Now, the terms for these, when they add together, it's called constructive interference. And when they cancel out, we call it destructive interference. All right? And these are generic descriptions of wave phenomena that involve interference. There's all kinds of other wave phenomena. Now, let's see. I'm going to have to I'm going to skip a few slides. Actually, no, let's keep going. Here's a diagram of something called beats. And I have this slide because I thought we did the tuning fork demonstration. When you have two tuning forks that are slightly out of frequencies, in other words, one of them is slightly flat or slightly sharp, then you'll get, if you hit both tuning forks, the sound will kind of go wah, 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 like that. It'll kind of wobble. it'll get loud and then dim, loud and then faint, loud and faint, loud and faint. And that's called beats. And it's because if you have two waves of slightly different wavelengths, you'll get places where the waves are really piled up, and then other places where you have destructive interference. Now, this is kind of a stinky sketch. It's useful, but here's a nice sketch. This one is one that I made. Okay, I took two waves, slightly different wavelengths, slightly different frequencies. So go ahead and make a sketch here. Here's sea level or equilibrium. And I made my two waves at two different frequencies, 106.7 hertz and 119.5 hertz. And I made like a snapshot. Okay, now they have different wavelengths. So I want you to make them look similar here at the beginning, but now if you get over to about here, right in here, look at that. The peak of the red wave corresponds position-wise to the trough of the black wave. Pretty close. So right about there, you're going to get destructive interference, flat water. But over here at the start, you've got peak to peak. All right? And over here, trough to trough. So that's good. That's constructive over here, but in towards the middle, destructive. All right, here's what it looks like. If you were listening to these two if it was audio signals at these frequencies, you'd be able to hear these. These would be fairly low notes. Okay? So not a really high C or anything like that, but you could hear this. Okay? This is what you'd hear. So try to make a sketch of this. Okay? Over here on the left, the waves over here are adding together. You get big amplitude. So write down big amplitude over here on the left side. Now, in the center of the blue wave train, this is the combination. This is you listening to both wave sources. Okay? So one speaker over here, one speaker over here, and you're right in the middle. All right? And this is what you're going to hear. Right here, when this part of the wave train gets to you, it's going to be pretty faint, very low amplitude. And loudness is related to the amplitude. So right here, in the center, right in here, it's pretty faint. Barely hear it. But then it gets loud again. And these wave trains, they come by you with regular faint, loud, faint, loud, faint, loud. And when you see, when I get the YouTube, you'll hear it. It'll go wah, 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 like that. It'll sound like one note, but it'll dim it in and out. Okay. Yeah, over here we got two troughs, right over here on the far right. See if I can get this. See right here? Two troughs, and boop, there it is. Yeah, okay. And in between those two places, you're getting a little bit of destructive and a little bit of constructive. Okay? So here is max destructive in the middle, and left and right is max constructive. Now, the frequency of the beats, the frequency of how it goes, wah, 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 like that, is just big minus little. In this case, F2 minus F1. And so that's equal to 12.8 hertz. And it just so happens that if you calculate this, and I'll show you how to calculate this on Thursday, 6.25 meters, that's this distance here. That's the wavelength of the beats. I didn't dismiss you yet. So the wavelength of the beats is right there, and it works out to 6.25. That's the distance between maximum amplitude to the next maximum amplitude. And halfway in between, minimum amplitude, very faint. Okay. I'm going to give you some homework tonight that's going to require you to look at this rail fanning video on YouTube. I'll link to it in homework. And you'll be able to listen to something called the Doppler effect or the Doppler shift in the frequency. And I'll ask you 1 or 2 questions about it for homework. Okay, you're dismissed. Homework will be ready tonight sometime after supper. You're dismissed. See you on Thursday.